Okay, so in part C here, what we're doing is we're looking at inside chapter 23 in Bio 212 from Norwalk Community College, AMP2. You're looking at in the alveoli of the human lung, how exchange of gases is going to occur. And there's some law, and it's called Dalton's law, and you saw this inside your chemistry class way back when. And what I want to do is impress upon you that inside a mixture of gases, which is what the atmosphere is, each gas has its own personality. And it behaves as though there's nothing else around it. So if you think about like nitrogen here, it's pretty much inert. And even though we don't think it's doing anything, it obviously has a very important role in occupying space to make sure that the concentration of, say, oxygen, which is very reactive, versus carbon dioxide, which tends to hide, literally goes into solution really quickly. Each of these personality types, the plasma of our blood, the capillary beds themselves, and then the individual cells that absorb and or respire these gases, takes advantage of each of these personalities. And that's what we're talking about here. Each actually has a specific partial pressure as a result of those behaviors. And the sum of these is how we calculate the total atmospheric pressure at 760 millimeters of pressure. Okay, and you can see how this happens inside this slide right here, where you're looking at roughly, whoa, I know what I just did there, and I shouldn't have done it. Damn it, man. Anyway, okay, roughly, what is it? 78% of all of the gases that are inhaled are nitrogen, 20% are oxygen, 0.4% are water, 0.004% are carbon dioxide. And this is what I mean by a very small concentration of carbon dioxide outside of the body, but a fairly high concentration of carbon dioxide outside of the body that will actually have to travel inward. And Mother Nature takes advantage of that because Henry's law states the quantity of a gas that is dissolved in a liquid is proportional to the partial pressures of that gas. And you're what again? You are a bag of salt water. So let's put that in there. Bag of salt water, which means that all of these gases have to dissolve proportionally inside that space. And the higher partial pressure of a gas over a liquid will change its solubility, so the gas will stay in solution. And by what I mean there is, remember I said carbon dioxide is more soluble? Well, it's not only just more soluble, it's 24 times more soluble. So that means the waste product of normal respiration can easily be moved into the plasma of your blood to get it away from a mitochondria. And this is really important when you're thinking about what happens to waste. If you clogged up the exhaust system in your car, it would eventually stop running. And that's the same thing that happens here. Okay, so we have to figure out a way to take advantage of the fact that carbon dioxide needs to be moved out of the body as quickly as it can. In class, I'll go over to what the bends are and stuff like that, but how do we actually regulate external respiration and internal respiration? And one thing I want you to think about, I'm going to try and draw this, and of course I'll muck it up so you guys can all laugh. So outside here, here's you, right? This is you. You are a human body, not even in correct anatomical position. Put your hands down your sides here, right? And here are your lungs. That's a lung and that's a lung, right? And here's where external respiration is occurring, where you are inhaling O2 into the lungs, and then you're going to exhale carbon dioxide out of your lungs. Okay? What's going to happen here, of course, is you're going to have that come in at a specific pressure, 105 millimeters. Okay? It travels through the capillary beds to 45 millimeters. You'll see how this looks in just 2 seconds. Whoops, let's go back here. Let's go back to this one here first, right? And then diffusion is going to occur at the capillary bed, and it's a mixture. And the small amount of mixing of blood in the conducting portion of the respiratory system will actually drop the partial pressure such that inside the pulmonary veins, it's about 100 millimeters of pressure of oxygen. And you'll see the significance of this. Likewise, you have the almost opposite concentration effects. Because remember, not only do we need to get rid of carbon dioxide, but we need to make it more soluble, or Mother Nature's already taken advantage of that, and you'll see how. That's all there's the external stuff. You got to get it out of the body. Internal respiration is when oxygen is going to travel actually into the mitochondria. The carbon dioxide actually exits out, and at rest, take a look at this, 25% of all of the available oxygen is actually being used. That means deoxygenated blood would retain 75% of its own oxygen capacity. So if you've ever had an pulse ox 2 on your finger, right? That is somewhere between 98 and 99% for the normal healthy human being. And most of that is because 75% of all those possible oxygen binding sites are already occupied most of the time, which means all of your physiologic needs can at rest be taken care of with that 25%. So here's a fairly decent cartoon you actually have inside your textbook where if this is inside the alveoli of the lungs, this is now internal pulmonary respiration where the gases have come in, oxygen comes in, and notice its pressure, travels to the actual systemic capillary beds where now you're going to feed the mitochondria inside here. Notice the pressures have changed, 40 and 45, and now carbon dioxide comes out and it travels easily out into the alveoli because look, its partial pressure inside the atmosphere is essentially 0.3, but it's 45 millimeters inside the body. So this is a steep concentration gradient here that allows carbon dioxide to actually get out of the body. It's all going to depend on the partial pressure of gases and what you can actually do to change those. And of course, what you can do is you can change the surface area, you can change the diffusion distance, and the molecular weights of the solubility of those gases, right? So oxygen has a lower molecular weight and should diffuse faster than carbon dioxide when diffusion is slow, okay? And the body actually takes advantage of that, and we'll see how in a minute. Okay, so this is a true statement. Oxygen transport has about 1.5% of oxygen transporting inside the plasma of blood. And you can think of this as maybe feeding the endothelial cells. But large vessels actually have anastomosing circulatory systems to make sure that's taken care of by the actual connective tissues below them. But that means 98.5% of that oxygen is actually bound to hemoglobin. And you remember what hemoglobin looks like. Let's see if we can draw this for you here. Right? Let's go like this, go down here. Hemoglobin was 2 alpha chains, 2 beta chains, and remember there was an iron binding center inside each of these. And you had 280 million of these inside each red blood cell, and you can all do the math, right? So let's do that. Okay, so if we remember that from chapter 19, let's go over here. Let's do this. Whack. Okay. Hopefully you also remember that you have those 280 million that could bind here inside each red blood cell. Now what this slide is telling you that most of, so this is a red blood cell here, right? And remember inside class I sort of moved through that capillary bed. Remember, squish, pull, squish, pull. Well, what the hell happened there? I didn't even touch anything. This is what happens. I'm starting to get pissed off with this. But anyway, here's the capillary bed. So what's going to happen is the microenvironment here is going to change, and that's going to change the binding and the dissociation of oxygen from hemoglobin, which is kind of cool, because what Mother Nature does is she creates the environment for which this is going to actually happen. Let's do that. Let's get out of here. Let's do that. Okay. And let's go here. Let me show you what I'm talking about. Let's go here. So here is oxygen that is bound to red blood cells at essentially 100% saturation. All right? And here is deoxygenated blood. Follow this line all the way down, where you actually have active contracting skeletal muscles. And what this is telling you is that in those areas where work is being done, oxygen is of course being needed, and that means that oxygen needs to be made available to it, right? Meaning to the mitochondria inside those multinucleated, multi-mitochondrial assisted skeletal muscle fibers. And this point of inflection here is where you actually have deoxygenated blood that's actually traveling inside the circulatory system, inside the veins of the body. And remember, that's about 75%. Okay? So this is that 25% difference. So what's really going on here is actually kind of cool. Okay? Other factors affecting the affinity of oxygen have to change how oxygen binds to hemoglobin. So let's draw this stupid thing again. Keeping my fingers away from the controls that actually change the shape of the slide. Trying really hard at least, right? Okay, so here's our hemoglobin. So this is one hemoglobin molecule, 2 iron binding sites here, 2 iron binding sites here. And let's just remember these have oxygen because they've left now the aorta and they're going to travel to some muscle, say inside your big toe, right? And you're wiggling that big toe, which means you need oxygen to actually allow that to happen. But before you even need the oxygen, remember, here's the cell, right? And it has mitochondria. I remember the waste product of mitochondria is going to be carbon dioxide. And this is what they mean when they say each makes sense if you keep in mind that metabolically active tissues need oxygen and they produce acids, primarily hydrogen proton. And you'll see how in a second. But that hydrogen proton is being made as a result of the carbon dioxide waste. And because these muscle contractions are shortening the distance between 2 points, remember, thin filaments, thick filaments contract, pull A towards B. This generates heat. And this acidity, as well as increasing concentrations of carbon dioxide and an increasing temperature, will now allow oxygen to now move off of that hemoglobin more readily. It's called the Bohr effect. And once you get one oxygen to move off, the second one moves off more easily, the third one moves off, and then here we go again. I didn't even touch a bloody thing, and the slide got smaller. Let's go see what happens when I do that. I'm going to do that. There we go. That goes back to normal. I put the pen down because I'm tired of making mistakes. Okay? So having said all of that and removing the cartoon for you, let's take a look at what happens. This is normal blood pH, 7.4. It's the average between the low pH, which is 7.2, which would be slightly acidic or more acidic, and high alkaline blood. And notice what's happening is the more alkaline you are, the more oxygen maintains its affinity for hemoglobin. The more acidic you are, the more oxygen releases its affinity for oxygen. Okay, meaning hemoglobin. Likewise down here, as you are, so this is increasing numbers of hydrogen protons. As you're making more carbon dioxide, look what's happening. You could superimpose these things on top of one another, and you're like, hey, that's kind of cool. I know what could be causing that. And your answer would be correct. One more thing to throw in there before I go to this next slide is take a look at the fact that once upon a time I told you that fetal hemoglobin, of course, has greater affinity for maternal hemoglobin. And this is actually how, when that blood goes to the blood sinusoids adjacent to the placenta, this is how the fetal hemoglobin binds all that oxygen and brings it back to the fetus. It outcompetes maternal. It outcompetes maternal hemoglobin for that carbon dioxide. So how do we actually get this stuff to attach or relax or let go of? Well, it's because we are making carbon dioxide. Most of it is dissolved directly into the plasma of blood. Some small amount of it binds directly to those amino acids, including hemoglobin, to make carbaminohemoglobin. But here's where something should start to sound familiar to you. 70% of it is transported as bicarb. Okay? And what we're going to do is we're going to use carbonic anhydrase again for the umpteenth millionth time in this class. And we're going to form carbonic acid, which is going to dissociate into that acid hydrogen proton I was telling you about a moment ago, and the bicarbonate. Okay, whoops, we just switched them around. Okay, maybe it's more important that the hydrogen comes first, but here's the idea. We're going to finish this slide off, and then we'll start again in sort of a review section. Maybe I'll just try and muscle through this. Here's the equation I've been writing on the board since the first day of class back in A&P1. Here's carbon dioxide plus water, because you are a bag of salt water in the presence of carbonic anhydrase. You should put a Ca up here, right? You make that carbonic acid, which then spontaneously dissociates into bicarb over here and hydrogen protons. And this is what actually causes the shift to allow things to move. But how does it work? Here's a figure we're going to spend a great deal amount of time working on. And what happens is, of course, you actually create this thing that's called a chloride shift, where we have to maintain a charge across the membrane of the cell. Across the membrane and inside the cell as well. Okay? But take a look. Let's start with carbon dioxide production inside tissues, right? That big toe you're flexing. Carbon dioxide's being made. Chloride moves into the cell with the carbon dioxide. In the presence of carbonic anhydrase in the water, you make that carbonic acid. The hydrogen proton pushes the oxygen off, such that oxygen can keep that cell alive. We now collect that carbon dioxide in its 3 different populations, right? We travel back up to the lungs, and lo and behold, take a look what's going to happen. Inside the lungs, we have a low concentration of carbon dioxide over here and a high concentration of oxygen, so carbon dioxide wants to come out. How does this happen? Oxygen comes in, it pushes the hydrogen proton off of hemoglobin. That hydrogen proton, in the presence of carbonic anhydrase, will take that carbonic acid and convert it into water and carbon dioxide. At the same time, the carbaminohemoglobin is going to be letting go of that carbon dioxide, creating a great concentration of carbon dioxide, such that it moves out as you exhale it. Notice what happens to those chloride ions. So to sum this entire chapter up, really what you're doing is you're inhaling and exhaling to get rid of carbon dioxide. And the way you change that is by changing the total number, don't know what happened there, changing the total number of hydrogen protons that are present. And you change those total number of hydrogen protons because of the amount of carbon dioxide you've made in metabolically active cells. So these 3 pieces, A, B, and C, have been chapter 23 inside Bio 212 at Norwalk Community College, right? And there's a lot of small details inside here. So again, you've listened to these, you've read the textbook, and you're thinking to yourself, how does Mother Nature do all of this? What really is the goal? Well, the goal, of course, is you can't break down glucose unless you have oxygen. At least you can't break down a whole lot of it. And you need to break down a whole lot of it to make energy to stay alive. So take this previous slide, sort of go back and take a look at it. What's the piece that's missing here, all right? These are waste products. Remember, those waste products came from normal metabolism, okay? It's a pretty good place to finish, so that's where we'll stop. Have a great night.